scusami, questa cosa la devo mettere, ragazzi, non so scrivere ora la metterò, mi
Okay, I am ready. Everything is fine. Any question before I start? Okay.
Professore, possiamo chiedere se lei conosce il professore del Politecnico che ci terrà lezione la prossima settimana?
Non lo conosco, mi dispiace, no. Però ho una mail.
Noi infatti se possiamo avere il suo contatto, perché vorremmo provare a chiedere di spostare la lezione, solo che la
Okay, so I'm not sure if you noticed, I uploaded the video of last week, which is working fine, and maybe you don't need it. But in any case, just for your information, today I have a technical problem with the computer here in the room, so I am recording with my notebook. I hope that it works fine because I don't have access to the wireless here, so I'm connected with the hotspot of the phone. But in any way, okay, so far it works. And so I just have to remember to share the screen in both in the PC and everything, but I think I can manage it. Okay, so today, let me just go to the last week lecture. So introduction, here we are. So I think we got to this slide here, just a second, this one maybe. I think we discussed already of the impact of global warming. Did we discuss also of climate change, weather extremes, and the sea level rise? Did we get to flood and droughts? Do you remember? Did we already discuss about this? No, okay, perfect. In any case, it's quick. So, okay, let me just expand it. Okay, perfect. Just 1 second, because I have to remember to move to also on the notebook. Otherwise, okay, that's fine. Perfect. Okay, and here we are. Here we are. Okay. Lecture notes, okay, and introduction. And then I give you a summary of what we are doing today. So, okay, perfect. Okay, good. So, today we get into a more detailed discussion about climate change in order to recognize what climate change means in detail with a more scientific approach, and then to discuss how we can model climate change. The purpose is to give you a basic knowledge of how we get information about the future climate, because this is the basis for planning. And in your case, this is the basis for devising strategies for coping with the additional risk for health risks induced by climate. So first of all, we have to understand what we mean with climate change, what we are expecting for the future. First, from a qualitative point of view, and this is what I'm doing with these first slides. Qualitative means more or less, in order to get the big picture. And then we will get into more details, and we will also talk about modeling, because it's not an information that you directly need, but it is useful for you if you know what are the theoretical basis, also just some information, not really the details. What are the theoretical basis for predicting the future climate, what we are expecting. Usually our predictions are extended up to 2100, okay, so about 75 years from now. Okay, so first of all, let's start discussing, and then I anticipate in the other two lectures we will discuss in more detail about the health risks and the illnesses that are related to climate and climate change. So we will get more into your field, let's say. So in order to start, the first, let's say that the effects, the implications over human health of climate may be related to illnesses, communicable or non-communicable diseases that may get more hazardous, more risky, more widespread with climate change. For instance, if we talk about malaria or cholera, with the increase of temperature, there is an increase of concentration of mosquitoes, and then probably enlargement, an increase of the extension of the areas that may be subjected to malaria. So there is a risk that is related to diseases. And then there are basically three categories. The first is health risks related to diseases. The second category is traumatic consequences. So you get flooded and you get injured. So it's a problem that has a traumatic origin. And the third category is mental illness. Because, you know, with climate change and with the occurrence of extreme events like floods and droughts, also people have severe psychological consequences, which may bring mental disorder, mental stress. And this is actually a risk that is increasing more and more nowadays. Probably it's also increasing because we pay more attention. Past we didn't care much about mental disorder because it was accepted, more accepted, like a normal consequence of a difficult situation, a difficult life. And today we are paying more attention, we are monitoring more, and then we realize that indeed it's a huge problem. So I talked about extreme events. So these extreme events are basically the main driver for traumatic events, traumatic risks, risks due to trauma, and they are also the main driver of stress, mental disorders, etc. And in particular, when we talk about extreme event, we talk about the events related to water. So extreme rainfall, extreme precipitation, excess of precipitation, and then flooding. We may have a direct effect given by precipitation, which is, for instance, when with the hail, we may have a traumatic damage because, you know, today we experience sometimes very big balls of hail. Hail means iced rainfall, you know, what we call grandine in Italian. I hope my translation in English is correct and understandable to you. And so it might be a direct consequence, but then water also has an impact on humans through flooding. And so there is a component related to extreme precipitation, and there is a component related to also the rainfall water transformation, rainfall flood transformation. So while precipitation is just an atmospheric event, which is strictly related to climate, when we talk about flooding, there is also an atmospheric component which gives the input, but there is also a transformation, a process intervening, which is the transformation from rainfall to river flow. and therefore it is more complicated. And when we talk about rainfall, we talk about a variable, and this is extremely important for you to understand, that is more difficult than temperature. What do I mean with difficult? I mean temperature is slowly varying. The variability of temperature, variability in time and variability in space. We talked about last week about time scale, spatial scale. So temperature is slowly varying. If you look at a graph of temperature, it is smooth. Okay, of course, if you look at long time scales, you see up and downs like annual temperature. But usually, if you look at the daily temperature, it is slowly varying. You don't have drops, sudden drops. And the same if you move in space. It is unlikely that if you move like 5 kilometers, you get minus 10 degrees with respect to the previous location. This is extremely unlikely. Okay, with the rainfall, the situation is precisely this one. So you may move like 50 meters and you pass from an extreme rainfall to like normal situation. And also in time, sometimes we have storms that last for 30 seconds, but still they kill people. Okay, and especially in urban areas. So rainfall is really more difficult to understand and model, and also to manage during emergencies. When we talk about wind is a little bit easier. Okay, even wind is not really homogeneous, but on the other hand, it's a little bit more, it's a little bit easier. When we talk about floods, indeed, there is the complication of rainfall, and there is also the complication that the behavior of the land have an influence. So if it rains over a paved area is different with respect to the situation when it rains over a forest. It's much different. And of course, the land behavior is also inhomogeneous. It is changing rapidly. And it's also changing in time rapidly because, you know, during this time, we see very rapid transformation of the land. And of course, this contributes to increasing the complexity. So the problem becomes more complicated. This is why when we talk about future temperature or global warming, we have a clearer idea. When we talk about rainfall, you may see that the scientific community has different opinions. Like somebody says it is not changed much. Somebody says it changed a lot. And so the reason is that, you know, depending on the area where the study was carried out, depending on the timing, there are significant diversities in the results. And therefore you can once more understand the importance of the local context. Okay, so flooding. You know that in Bologna we experienced some urban flooding last weekend. Fortunately, I mean, I can't say fortunately, one person died, but I said fortunately because if we compare with what happened last year, 13 persons died, and last year in May in the Romagna region. And the reason was indeed an extreme rainfall, which was really local. So if you look over Bologna, Bologna suffered while other cities around didn't suffer. And you may wonder why Bologna suffered and Imola didn't suffer. So there are two possible explanations. I can tell you that the rainfall over Bologna was really extreme. And if we look at the rainfall depth, which means that if you put outside like an empty tank, after 6 hours, you would find there something like close to 2 centimeters of water. And you may say, okay, it's 2 centimeters is not that much. But if you imagine 2 centimeters over a city, you understand that in terms of flow into the sewer system, it means a lot in about 6 hours. And people estimated, that some of my colleagues, that rainfalls like the one that Bologna experienced during the weekend didn't occur in the past with similar behavior, didn't occur in the past 8 years. So they have data for 8 years. They looked at the rainfall accumulation in a time of window of 3 and 6 hours, and they concluded that in the previous 8 years, they didn't have similar. So this is the most relevant event, the most extreme event in the past 8 years. 8 years, by the way, in a geological time scale or in atmospheric time scale is not a long time scale. So, I mean, of course, these are, when we talk about extremes, the rainfall in Bologna, they estimated, my colleagues, that occurs on average, a similar event may occur once every 200 years. So it is not a surprise that it occurred, the most extreme event occurred and never occurred in the previous 8 years. When we talk about frequency, you have had some background about probability. So maybe that you don't hate probability like engineers do. Engineers usually don't like talking about probability. I'm
just curious to know why.
Because, yeah, because for two reasons. Okay, in the scientific community, let's talk about the scientific community. Sorry?
I think doctors software, I think it's at the basis of any sort of empirical scientific.
Yes, this is true, but you know, the discussion on probability goes back to quantum mechanics. I mean, in physics and engineering, which is directly related to physics, there has been recently a movement towards, a trend towards deterministic modeling, because the trend aims to the perfection, so perfect deterministic representation. So the idea is in the scientific community to try to improve your knowledge of the process and describe it deterministically. You know that a deterministic model is the opposite of a probabilistic model. So this is one reason. And indeed, in practice, in their usual practice, engineers are used to deal with probability. So they don't refuse using a probabilistic approach for estimating, for instance, the risk of earthquakes, the risk of flooding also. But still, in the scientific community, there is a push for the risk of flooding to try to move towards a deterministic approach. I tell you that I like probability very much. I based my research activity on uncertainty assessment for these kind of models, flood models. And very frequently when I go to conferences, people say, ah, but this is old stuff. We have to move towards deterministic modeling, improve our knowledge, improve. So this is why I said that they don't like. And also engineering students, when they get the lectures on probabilities, they don't like it. When I teach to my students, I mean, when I talk about probability, it's really difficult. And this is a different reason. I think they don't like it because it looks like something caustic, you know, something nasty, something that is not nice to study. And I know that in medicine, the approach is completely different. Sometimes I bring the example of medicine. Also to my colleagues, when they say, we need a deterministic approach, I reply by saying, but look at your body. Would you accept a deterministic approach? Would you take a medicine, a treatment that has not been probabilistically tested, just basing on a deterministic model of which you don't know the uncertainty? So I'm bringing this example.
Wow, thank you so much.
Yeah, it is interesting, by the way, but still. And so let's go back to floods. So it is difficult to describe them. It is not easy. So basically, what can we say about climate change and floods? We can say that for sure, I mean, there is the feeling that the flooding is increased. If you look at the damage by flooding, statistics are available on the web, you see a clear increase. And in the past 30 years, there is a clear increase of damage, but also flood frequency is increased. So what is the reason? Climate change, probably. Still, we need to make a difference. Climate change, now we understand that probably has increased the risk of flooding in small catchments. Catchment, do you know what it is? It's a river basin, drains an area. A river takes water from an area, a portion of the geographical land surface. And this area that is draining to a river is called catchment or river basin. Okay. So when the river basin is small, which means the river is small, yes, we can say now, based on the data, that climate change has increased the risk there. For large basins like the Po River, the Arno River, we are still not sure. It seems not, because if you look at the Po River, for instance, we had two major floods, but not an overflow. But we had two significant floods in 1994 and 2000. But after 2000, the Po River didn't suffer from any flood. And the same thing if we look at other big rivers in Italy, like Arno, like the Tevere. But for the small catchments, if you look at the list of floods in Italy, there is in Wikipedia, in Italian Wikipedia, there is the Lista delle alluvioni italiane, and you see at the size of the catchment, which is reported there, you see that indeed the recent floods occurred in small basins. Why is this? This is interesting because the small basin, it reaches critical conditions for short rainfall. This may be something that you understand, that you get. When does the Po River get in critical condition? After 1 week of rain. So if it rains for 1 day, the Po River doesn't care. Okay? If you look at the urban areas, like the flood that we had in Bologna, usually they don't suffer if rain lasts for 1 week. They suffer from small duration, short duration rainfall, like Bologna, 3 hours. This is interesting, and you may say, why is this? Because it is, I try to say it in a few words, because when the rainfall event, the extreme rainfall event is short, it is more intensive. Think at the summer rainstorm. You get completely wet in 10 seconds, something like really, wow, very intensive, okay? If you think of a 1 week rainfall, it is very short intensity, very small intensity. Like today, you see that it rains, but it's not very intensive. Before getting wet, you take a long time. So what is, this is quite easy to understand. On the other hand, if you think of a small river, after it rains, it starts raining, you see an immediate reaction. It means that the small river has a response time that is very short. So think of a very intensive short time rainfall over a short river. So the rainfall lasts like 1 hour, but the river after 1 hour has already responded. This means that a very intense rainfall falls over the river, which responds soon. So big flood. Over the same river, if you have an intensity of rainfall that is very small, then the river doesn't care. Okay, so you understand that the small river, of course, it is more dangerous with short rainfall, more intensive. Now think of the Po. The Po takes 1 week to respond. So if you have a very small rainfall, first, a very short rainfall, which is very intensive, but it's very short. First, usually this very short rainfall is very local. Think at your experience. Summer thunderstorm is very local. Like today, it's very extended. So the Po River, local rainfall, even if it's very intensive, doesn't care. And the Po River takes 1 week to respond. So you can understand that in 1 week, there is time for this very intensive rainfall to, in a way, to slow down. To slow down while it travels towards the river, to get attenuated. So it is the connection between the duration of the rainfall and the response time of the catchment. When they are the same, the catchment reaches a critical condition. When they are different, the catchment doesn't care. So the meaning is that short basin, short response time, short rainfall is the problem. Large basin like the Po, long response time, we need a long rainfall. So this is why we can say today that only the short basins are suffering for climate change according to our data. Why? Because it looks like only short rainfall has been influenced by climate change, by global warming. Short rainfall indeed became more intensive. How much? Something like around 10%, and this is an order of magnitude. I think I already gave it to you last week. This is an order of magnitude. 10% more is significant. Of course, when I say it's an order of magnitude, keep into account that it's not the same everywhere. Again, the local context. So you see that for short catchments, we can find really an understandable, scientifically based explanation of the impact of climate change. For the big rivers, it looks like, also if you look in Europe, it looks like it's not so bad. It's not so bad. Okay, so, and this is what is written here. In my speech, in my talking, I was more detailed with respect to this slide, okay? And keep in mind one thing, that we still have, especially, let me see if droughts are treated later on. I don't remember, just 1 second. Okay, it's treated here. Okay, let's move forward. Let me say one thing. There is one feature of climate that we still don't understand. It looks like, if you look at the data and our experience, it looks like sometimes we experience flood-rich periods in a given location. So it looks like these events appear in clusters, and we don't know why. And also for droughts, it appears that these events occur in clusters, and we don't know why. Typically, we explain this feature by saying that there are some dynamics of atmospheric processes which we still don't know. In particular, we don't know details on the memory of these processes. Okay, this is important to know because it gives to me the opportunity to introduce an additional consideration. We don't have a full understanding of climate, and I stress the concept which I already mentioned to you last week. We don't have a full understanding of climate, and in particular of some feedbacks. Feedbacks means a reaction of some, like the reaction of the ocean to warming, or the reaction of the atmosphere to warming in terms of changes in the dynamics of clouds, perturbations, etc. And this brings me to say that we also don't know the reason of these clusters. So, for instance, one of my colleagues on Monday told me, look, we have had 3 floods in 2 years, 2 very intensive rainfall events, in 3 very intensive events in 2 years. So it is a sign of climate change. And I commented by saying, yes, but you have to take into account that these events sometimes occur in clusters. So you get like some years where you don't get any flood event, and then suddenly you get many of them concentrated. And this is also valid for droughts. And for droughts, there is an additional problem that indeed the description of the flood, it is something that it is much easier than describing a drought. Why? Because the drought lasts for a very long time. So a drought is not a drought if it doesn't last like some months. The flooding, it's much shorter in terms of duration. And therefore, to describe these processes, which have a large extension, so involve a large part of the atmosphere, is not just a local phenomenon. And then last for, sometimes they last for 10 years. And I give you some examples. In Australia, from 2000 to 2010, they had 10 years of extreme water scarcity. They get much less rainfall for 10 years. And then their reaction was that they started to build desalination plants because they needed to get water from the ocean. but desalination is very energy demanding, so it's a bit of a problem. And now these plants are not used anymore because they don't need as much water as they needed for 10 years. There are plenty of examples in the literature about these events. If you look, if you are interested, just out of curiosity, and you look on my, just 1 second, on my website, there is an introductory book for students, a travel through time to explore past and future mega droughts. And it was just something that I did for fun. I reconstructed the history of several mega droughts that occurred, and sometimes they lasted for 100 years. It is really something. Yeah. About 1200, there was a huge drought in Europe. And this is something that we don't understand. Okay, let me just go back here. Of course, these events can be, in a way, we can get prepared, can be the risk induced by these events can be mitigated. And flooded drought risk in particular can be mitigated by measures, structural measures. So for instance, dam constructions, because to cope with water scarcity, usually humans build reservoirs to store water when there is plenty of water in order to have a reserve for the water scarcity periods. And also for floods, we can get prepared in the urban areas by for instance, adapting our houses in order to make them waterproof. This is used in many situations. And there might be also non-structural measures like what are called nature-based solutions, like increasing the forest coverage or using green roofs in order to reduce the amount of water that goes into the sewer system, or try to infiltrate the excess of water into the ground instead of delivering the excess water to the river or to the sewer system. So it is, there are ways to adapt, and therefore we talk about climate change adaptation, which means accepting climate change and trying to adapt to it. And this is also something that we can do on the health side, getting adapted to the changing conditions, changing risk conditions, risk for health conditions. We can adapt. We can adapt with prevention, preliminary treatment, vaccination. There are several ways to get prepared also in terms of the health system. We will discuss some of these measures in general. And also climate change can be mitigated, but it is a completely different action. Mitigation means that we try to reduce the emissions of CO2 in order to reduce the greenhouse effect. Okay, let me go also forward with the other PC because otherwise I don't register. Okay, now there is a lot of literature also on hurricanes. Hurricanes, it is again very complicated. And in this slide, I show you two different interpretations. The conclusion is that with hurricanes, which are a relevant risk today, and you know, not really in Europe. Also in Europe, we are starting to experience some tropical events like tornadoes, etc. But you know that in other locations in the United States, in other continents, hurricanes are a real risk. So here you see first an interpretation from an ASA. Basically, they say that climate models predict that hurricanes will become more frequent and will cause more intense rainfall and an increased coastal risk. Usually the coastal areas or the areas close to the ocean are more exposed to this kind of risk. IPCC, on the other hand, which I will introduce in a moment later today, which is an international body of the United Nations who has the mission of studying climate change and proposing solutions, you see that IPCC, which is, I mean, a very unbiased body, which is not really keen on dismissing the risk induced by climate change. Absolutely, quite the opposite. IPCC is very keen to be conservative, and nevertheless, they say 10 years ago that globally there is low confidence in attribution of changes in tropical cyclone activity to human influence. So you understand that indeed it is something that it is complicated. It is in a way chaotic. It's very chaotic. Do you know what is chaos? Chaos means that the process is deterministic, but a small change in the initial condition of the process may completely change the final result. So this is, to summarize chaos, there is the famous quote by Lawrence, who said that a butterfly flying in Tokyo may cause a tornado in the United States, because he wanted to emphasize that a small change in the system condition may produce a huge impact very far away. And so with chaos, we mean something that is unpredictable, completely unpredictable, even if it is a physically based process. So in principle, it can be described by a deterministic model with certainty. But then there is so high sensitivity to boundary or initial conditions, so conditions at a certain time, that cause in the future a huge impact, even for a small change. So it is quite chaotic. Another story is sea level rise, and I think I already gave to you some orders of magnitude. So global sea level rise has increased about 20 centimeters, depending on the location, because it's not constant, from 1880. And about the recent increase in 2021, global sea level set a new record. It's about 10 centimeters over 1993 levels. It means that in 30 years it's increased about 10 centimeters. So it's an increase that you may say that it's not so relevant, but if you look at the impact actually of this increase on high tide flooding and the impact in terms of saltwater intrusion into the land, it is a significant impact. It is something that is not really negligible. And keep in mind that sea level salt intrusion causes severe health implications. It causes implications on the ecosystems, but also on the human health. Of course, we hope that the quality of water is controlled, but in some countries, maybe not so controlled like it is in the Western world. So people may start drinking water that with high salinity, and you know what are the consequences on the human health. And this is a topic that is highly investigated by science. So to what extent we can tolerate the use of water with high salinity, for instance, in irrigation, because there is a threshold beyond which the ecosystems die. But in Israel and, for instance, in the Middle East, in general, they made experiments because, desalination is costly, and it costs more for high degrees of desalination. So they are studying if it's possible to use irrigation water with a lower desalination, because this allows them to save energy, reduce emissions, etc. Okay. There are some positive impacts of climate change. Why positive? Because, it's clear that if you have a change in climate, it gives negative implications, but it may also give positive implications, because there are lands that could not be used by humans in the past, and now they become prone to agriculture, prone to human settlement. Of course, we are more attentive to the negative impacts, but there are also positive impacts. And here you see some examples: less mortality for cold waves, or decreased avalanche risk in some regions, or earlier onset of the growing season, a more extended growing season. For instance, some people made a research and demonstrated that the quality of the wine in France has increased because of the higher temperature, the the level of sugar into the grapes, you know. So
it's much sweeter now.
It's yeah. You know, it is also the alcoholic level is increased, because with a warmer climate, you have more alcohol into the final result, into the wine. And I think it is for the increased level of sugar. It's related to that, I think.
Yeah, because of the fermentation.
Fermentation, yeah. Okay, you know better than me. Okay, and also tourism. Okay, and may benefit from a longer season, not skiing, but the other form of tourism, yes, they can benefit. And shipping commerce may benefit from longer seasons, where longer time windows where they can navigate. For instance, the opening of the Northwest Passage for longer periods, and also expansion of agriculture in the north regions. Okay, so let's try to get into more details then. So how do we study climate? So what I provided so far, it's a big picture, okay? And we talked about the main implications in terms of impact over the humans of climate change. So warming, hot waves, and floods and droughts. Also cold waves, because, you know, there is a reaction of the climate system, so that in some of the regions you get also an increased risk due to cold waves. Flood and droughts, hurricanes, and also we didn't talk about landslides, but landslides are another risk, and sea level rise. Keep in mind that today there is a trend towards attributing several more implications over the humans and the environment in general due to climate change. Sometimes there is a bit of exaggeration, but on the other hand, I think it is useful to know that some people have studied the effect of climate change on societal systems, like migration, political instability. Other disciplines, they are studying the effect of climate change over the earthquake risk. And you may say, what is the relationship? The relationship is groundwater. So when you get a shortage of groundwater, and in several regions, indeed, they are experiencing a shortage of groundwater, especially in the Middle East, there is people prove that with reference to the United States, there is a relationship, a statistically significant relationship between water level, water table level, so groundwater level, and frequency of minor earthquakes. Of course, when we talk about huge extreme earthquakes, we don't have data to prove this. With more frequent earthquakes, by definition, if they are more frequent, they are less intensive. And they prove that there is some relationship, like it seems that there is a relationship between the frequency of earthquakes and gas extraction because of the impact on the internal dynamics, deformation of the Earth. So we provided quite a big picture, and the list of the possible implications of climate change is large. But as I said, let's focus on the main ones, but let's also keep in mind that there are other possible and several implications. So let's get into more details, and how is climate and climate change studied? I think it is interesting to mention the Intergovernmental Panel on Climate Change, IPCC, IPCC is a body of the United Nations, and it is composed by a large group of distinguished interdisciplinary scientists with a prevalence of atmospheric and climate scientists. And they produce a continuous assessment of the state of climate. And also they produce a continuous review of the progress of science towards improved climate modeling, climate understanding. They typically publish every 5 years, but the frequency is not fixed. What is called an assessment report. We got to AR6. AR stands for assessment report. It's, I think it is half published, and you can look on the IPCC website. There are all the assessment reports. The good thing is that, first of all, they produce a detailed report and a summary for policymakers. And the good thing is that, in general, the language is understandable. It's not really for the public, but it is a treatment that is not strictly disciplinary. So getting information, it's indeed a useful source of information. It is continuously updated, and for sure this is a reference that is trusted. So if you need in your future to refer to a scientific basis for justifying a prevention action, for justifying a strategy, for sure the reference to IPCC is trusted. They are a bit too conservative, as I said, in my opinion, or I mean, they stay on the safe side. So keep it in mind. As an engineer, for instance, I tend to say that if you stay too much on the safe side, you have two problems. First, we are likely to do nothing because we don't have resources. So if I want to design and build a huge dam for storing water because I want to get prepared against water scarcity, it may turn out that the environmental impact is too significant, unsustainable. And this is the second problem. The first problem, which I already mentioned, I don't have the money to build it. So as an engineer, I am aware of the value of the cost-benefit analysis, and we need solutions for sure. So these disasters that I mentioned are occurring, so we need solutions in any case, and we need to get prepared also to react from the health side to these disasters because they are occurring. So we need solutions. There is no doubt on that. So sometimes we debate what is the cause, climate change or land use change, and often I reply, no matter what is the problem, we need to do something. And to do something, we need to, in a way, to be conservative for sure, but also to be effective. So be aware of the fact that if you refer to IPCC, the predictions sometimes are very conservative, and I mean, it may be worth lowering the expectation for the sake of doing something really to solve the problem, for the sake of finding a solution. So sometimes, for instance, in my close to my city, they are debating because we need more water in a valley, the valley that feeds also the area of the Parmesan cheese, where the Parmesan cheese is produced. We need more water. And then people are debating because there are two possible solutions. A huge dam and one smaller dam. And when I attended this, I spoke 2 days ago with one of my colleagues, and I said, if you continue to struggle for the huge one, the end of the story is that we don't do anything. Let's build a small one so we get water. And then, you know, in the future, there will be time for making the big one if we see that the small one is not sufficient. But let's do something, because otherwise, if we struggle for the big one, it turns out that environmentalists oppose, and then it turns out that we don't have the resources, the government doesn't finance it. So let's move forward with the smaller one. And the same I would say to a medical doctor. So if you have an onset of something that is really becoming more hazardous, we need to do something. And if you look at the prediction of future climate and you see that you can't cope with the situation in 2100, let's solve the problem now. And then maybe that in 20 years from now, the situation is different. Maybe that we have more means. This is what it's important to do, in my opinion, to find solutions to the current problems. And, you know, sometimes we get stuck in discussions. This is, I mean, we live in a democratic system, which is perfectly fine. But at the end of the story, we also need somebody deciding. And if you look at the current also international political setting, the politicians are a bit reluctant to take unpopular decisions, to adopt unpopular decisions, because, you know, in a democratic system, politicians also care about consensus. But on the other hand, sometimes we need somebody deciding, and at the cost of becoming unpopular. So IPCC is a good reference. On the other hand, they are conservative normally. I mentioned that indeed the water-related disasters are the most impactful climate-related events. Indeed they are, and I just want to show you some statistics here. And so you clearly see what is, this is the costs of 2022 climate-related disasters. And you see only for 1 year, so this is not a statistic. And you see that indeed the hurricanes, okay, they are not strictly related to water, but in some way they are, because the problem of the hurricane is related to flooding usually. Europe drought, China floods, China drought, East Australia flood, a storm. Okay, this is not strictly related to water. Drought, flood, and hurricane. So here there is another question. This is very easy, so I don't ask your opinion. And because clearly is, yes, it is increased, but it's not clear what the drivers are. So the risk, yeah, the risk is increased of floods at the global level, yes, but still it's not clear what the drivers are. Okay, now we come to probability. So let's keep in mind that when we talk about climate science and we talk about floods, droughts, anything is dominated by uncertainty. And as I told you before, some of my colleagues believe that we should try to eliminate uncertainty, and we should try to rely on deterministic models rather than probabilistic models. By the way, climate models are deterministic models. But on the other hand, in the climate science, there is a huge debate about how do we estimate uncertainty for our models. Indeed, uncertainty is extremely relevant. In what we are talking about, uncertainty is playing a key role. I think also in medicine is playing a key role. So maybe that you are more used to deal with information that is not exact and that needs to be tested. And this is something that in climate science, sometimes it is a bit, in a way, dismissed, like model testing. Just to make you aware, climate models, when you test them in the reproduction of the past climate, they fail. And you may say, oh, this is possible. I tell you, it's possible. There is a long literature on that. They fail, and there might be several reasons. So they also say that climate models are made for prediction of the future, not for reproduction of the past. On the other hand, you know, other people say, but if you can't simulate what you know, how can you predict what you don't know? And so, I mean, there is a relevant uncertainty, and this is something that you have to keep in mind. When we talk about future climate, it's like some questions of medicine. So there is uncertainty. On the other hand, uncertainty, we know how to deal with it. But the problem is to recognize it and to find, and in climate science, we are still along the way, find a good approach, a good model for estimating uncertainty. Yeah.
Do you think said that climate is a deterministic model, and you said that in deterministic models you basically know all the rules of the system. Do you think you as a scientific community have all the knowledge of all the rules that rule out in the system, within the system?
No.
Because, for example, in medicine, I can think about the fact that, of course, it's not deterministic, because in most of the diseases we don't know maybe the molecular player or the genetic background of the disease, so we miss some pieces to understand the complexity of the disease, and so we miss some of the rules, let's say, and that's the question. Do you know all the rules within the system?
In short, the answer is no, we don't know them. And I think in a way you started an interesting discussion, and give me 3 minutes to give an extended reply, and then we make the break. So the example that you made of medicine is extremely relevant, because it is indeed recalled frequently in our community when we discuss about our knowledge of the rules. So basically, some of my colleagues, they say, I mean, we have the laws to describe the movement of water. So in a way, it is water cycle, okay? Description of the water cycle. The climate is a description of the water cycle. So some of my colleagues say there is conservation of energy, conservation of mass, we know everything. So we must become able to know the rules, to make a deterministic prediction. And then they say, like Einstein said, he doesn't throw dice. God doesn't throw dice. So when he determines the dynamics of the world, he takes decisions, and it doesn't throw dice. It's not casuality. So basically, sometimes I say, there is uncertainty, there is casualty in our description of, and they say, no, there is no randomness. Everything is deterministic. On the other hand, now I'm trying to develop this interpretation. Okay, I can accept it. So basically, when you tell me, do you know the rules? Yeah, the rules, we know them. It's, as I said, conservation of energy, conservation of mass. I don't think we have some players, some internal rules that we don't know, at least if we talk about water flow. On the other hand, I mentioned chaos, but let me say, on the other hand, think of describing how water moves in the underground or over the land. In order to apply the physical laws, you need a geometric description at a very microscopic time scale. We don't have it, and we will be able to have it in the future. Some of my colleagues say, yes, because we will develop monitoring techniques that allow us to see everything, like for the human body. Today, you know, you have something. Yeah. On the other hand, my reply is, no way. You will never be able to describe in this tiny details each drop of water. We will never be able to do that. So at the end of the story, our representation is affected by uncertainty. It will be forever. And if you don't accept it, you will never be able to provide a good probabilistic description of it. While if we recognize uncertainty, then we can make a probabilistic prediction, which is as useful as the deterministic prediction. So the way is the integration. And then to go into finer details, when we talk about the atmosphere, there are some rules in terms not really of physical rules, but feedbacks, which we really don't know. Like I mentioned last week, the groundwater flow from the land to the ocean is determining ocean circulation to a large extent. But it's impossible to describe it, so we don't know the feedback of groundwater flow into the ocean caused by a flood, for instance. So we don't know if this feedback is positive or negative. You know, positive feedback, I make confusion frequently. A positive feedback reinforces the signal, while a negative feedback, we will talk about feedback later on. A negative feedback, in a way, compensates. Yeah. shut down. So in short, no, we don't know the rules, or we can say that we know the rules, but anyway, the application of these rules will be affected by uncertainty to me forever. Okay, let's make a 15 minutes break. Okay. So a couple of slides to conclude this introduction. So first, I turned on the micro because I found the way to record with Teams with the main PC. So, but I'm not sure if the micro is working if the audio is working when the mic is turned off. So I prefer to keep it open if it doesn't make any echo. So a couple of slides to conclude this introduction with some very general remarks. First of all, what is science? I would say that you don't need to any comment on this. And it's important, I put this slide because in climate science, in the discussion about climate change, which is a discussion that frequently involves the public and not only scientists, there is the kind of trend, a kind of personal attitude to trust a lot on consensus, because it's a debate that is a bit controversial. It's a debate that is very articulated, and we don't have a lot of data about climate, so it is not easy to stick on the scientific approach that makes use of experiments. And therefore, there is the feeling, the habit of some people to trust the consensus, which is something that, in science, it's a bit delicate, because consensus is perfectly fine in politics, is perfectly fine when you decide a political strategy, but science actually should be based on an objective interpretation of the reality through experiments and data. And therefore, it is something that I really would like, when I talk about climate, I really would like to make this premise, to emphasize this premise, because I think it is extremely important. And therefore, I mean, this scientific approach should really require that models are validated, are tested, are, in a way, even if we have a restricted amount of information, it is important to stick on the experiment, on the data that we have. It's important to stick on testing, and it's important to account for uncertainty. And this is something that, in climate science, sometimes it is hard to prove, because it is hard to follow, because if you account for the current level of uncertainty in climate science, probably you also include, you don't exclude the option of no change. And of course, given that climate change is also relevant from a political perspective, if you include the alternative, the option of no change, some scientists think that the communication becomes less effective. I really think that if we claim and like to be scientists, we should really try to stick not on the consensus, but on the data, on the scientific approach. And this is why this slide is here. And also you see this question, because maybe that I am biased, but I feel that in the discussion of climate change, which is interdisciplinary, the role of hydrology is a little bit neglected today. And it is a little bit neglected because climate, the main field is climate science, atmospheric sciences. And when you discuss also in science of very important issues that have a very, very key strategic role and political role, then an objective involvement of a comprehensive involvement of all the relevant disciplines becomes not easy, becomes a little bit complicated, and so there is I think there is the risk that it becomes an approach that is not very diverse. You know that diversity has really big value, great value. So it's extremely important, in my opinion, that this issue is discussed really in interdisciplinary perspective. And this is why I was excited also to teach here, because I think that even one may think that it's not relevant to climate science, medicine, but I think that the perspective of a different field is always important. And I think it's not the last one, because here I am self-serving, given that we are moving towards now a more quantitative description. And given that I just said that it's important to stick on data. It's not open, I don't understand why. Okay. I want to give you an example of a research that I recently did. It is very simple in the methods. It is related to the Po River. So what I did was to try to put together a long series of observational flows of the Po River. And what was the reason? In 2022, the Po River experienced a severe drought. I was concerned because, given that I know that droughts sometimes they last for like 5-10 years, I was concerned because I thought maybe that this is the first year of a very long one. So I was a bit concerned. And so I started collecting the data, some of the data I already had. And I knew that a person working in Venice published in 2008, a person whom I never met, because he's I would say he's a climate scientist, a statistician. And I knew that he published a paper where he analyzed the river flow of the Po River with a very long series starting from 1807. And my data started from 1920. So I sent an email and I said, look, do you still have this series? Would you be interested in checking how extreme is the current drought with respect to this long series? And then we got in touch. It was really exciting. And we put together a series of monthly flows from 1807 to 2022, because we analyzed data until the last day before submitting the paper. And I think the series is very relevant and allowed us to reach some conclusions that I think are interesting. We tried with Nature and Science, but they didn't want it. But then Science redirected to Science Advances, which is still a journal with a high impact factor. Results. First of all, you see this table here. It's a list of droughts with the year. 2022 is the most extreme one. In terms of what? In terms of, if you look at the July river flows, 2022 is ranks first. If you look at the river flows of June and July put together, again first, and so on. First for any duration, we extended up to April, May, June, July. So it was indeed the most relevant one. But if you look at the month of July, what it is really concerning is that, and these are the 10 worst droughts, 6 out of 10 occurred after 2000, in a period of 200 years. So it's clear that the frequency of drought is increased, clear. Then the drought stopped, fortunately, stopped in May 23, okay? And now the Po River is very high, so we are no more in a drought, but still 2022, and the frequency of droughts is increased a lot. But what is interesting, I think, is if you look at the progress of the monthly flows in July, and you see my mouse here, and you see that there is a decline. It's impressive, especially after in the past 20 years. But if you look at April, May, June, and July, you see that the decline is less evident. And then it's not presented here. We analyzed only the flows of March and April, and we found an increase. So what is the moral of the story? If you look at the complex volume, the complete volume of river flow for the Po River, it is not decreased in time. But if you look at the flows of March and April, they have increased. If you look at the flows in June and July, they have decreased. So what's going on here? It's simple. It's going on that with global warming, snowfall has decreased. So the precipitation during winter is in the form of water. You get more flow in spring, winter, and less flow in July, because snow is like a reservoir. And this is really relevant. It means that in the future, if it moves forward like this, we will get during summer for the Po River, which is the most important season for irrigation and also for getting water from the Po River in general. In summer, we will get less and less and less water, which is indeed significant. And it is based on data, not on models. So, I mean, it is a clear signal that comes out from the data. Actually, we also looked at the models, and the models, unfortunately, don't reproduce this. I don't know why, because, you know, climate models, it's not my field, but actually they don't reproduce this. Or we found some encouraging results from the very last generation of models, of climate models. It looks a little bit better. I'm not excluding that in the future we will be able to get more and more reliable climate models. Still, we are a bit far from this result. Okay, and this is the last one. Now, I think, let me see, I think this screen sharing has been, let me stop screen sharing, and let me go to our previous page and to the list of lectures, and let's look for the second one, the climate change problem. And here I have a PowerPoint which I am taking. So you find the PowerPoint at the end. You can, 1 second, you can download it. It is a zipped file, but if you click on the file manager, then you get the PowerPoint presentation. The PowerPoint presentation, I think I already mentioned it to you. If you're interested in the future, in a way, going back to these lectures, my suggestion, look at the web page, not at the PowerPoint, okay? Because the PowerPoint is a summary, and it's useful for teaching, but not for studying. This is my feeling. Okay, let me just see. Okay, perfect. So let me just try to share the screen now. Okay, and let me check what is the best. I think here. This one, okay. And okay, let me see if I can. I hope it is shared. Okay. Okay, so this is a summary of this lecture. I will start by explaining how we realized that climate change was going on. And then I will try to give more details on the history and science of climate change. I want also to give you an overview of climate models, very basic, but just to give you the concepts. And then climate data, which are the basis for setting up climate models and understanding the past climate. Okay, so first of all, I think this one is something that basically I already introduced. I just want to say that climate change is a concept that is strictly related to the concept of sustainability. And sustainability, it's a concern that emerged for the humanity, for the full humanity, like 50 years ago, in the mid of the 20th century, 1960, basically, after as I mentioned last week, after the economic boom, after what I said last week. After the Second World War, we had an international effort to promote recovery, which originated the economic boom. And the economic boom was based on exploitation of natural resources, which is perfectly fine. I mean, the whole history of human is based on exploiting natural resources, which is, I mean, perfectly fine. On the other hand, this exploitation was uncontrolled at the beginning. And therefore, there was a strong increase of the use of fossil fuels, of the use of water for producing energy, because also energy production started in a very significant way. And also the public health system developed significantly, and also the welfare developed significantly. But on the other hand, about at the end of the 60s, at the international level, in Italy a little bit later, we realized that we had in a way to take care of the environment because there were sustainability problems. Sustainability is defined as our capability to make sure that the environment can be exploited by the future generation with the same opportunities that we had in the past and we have today. This means sustainable. It means that our use of the environment, let me adopt this term, our use of the environment can be sustained by the environment, can be, in a way, in the future, can be used in the same way. Again, this is a concept that emerged only around 1970. And in 1972, there was the first international conference on sustainability. It was called in another way. It was called, I don't remember, but it was a conference on the preservation of the environment. And to give you an idea, in Italy, the first law on the regulation of the quality of the sewer systems, the first law that imposed also to administration to monitor the release of contaminants in the sewer systems was approved in 1976, Legge Merli. It was the first one. And the first law recommending, imposing the release of a minimum flow downstream, downstream river diversion was approved in 1989. So 1989 is the day before yesterday. I was already at the university, close to getting my degree. So, I mean, it's really the day before yesterday. So you can understand that it's a recent concern. And Agenda 2030, which means the Sustainable Development Goals, which I think you know about, they were approved, if I'm not wrong, they were 2030, Agenda 2030. They were approved in 1992, I think, or maybe even later. So it is really something recent. And then climate change is a part of the sustainability problem. At the beginning, the concerns were not really related to climate. They were related to water quality, both groundwater quality and surface water quality. The concerns were related to the ozone hole and acid rains. And then these problems were partially solved, and then climate change emerged. And you can see the sign of climate change in many footprints. Here you see some pictures related to glaciers, one picture related to water level in the reservoir, and there is also bottom right a picture of the circulation of water in the Pacific Ocean, which is a driver of climate, determines El Niño, La Niña, which are these large-scale atmospheric circulation patterns, which are determinants for climate in several continents. So you see the fingerprints in several environmental processes. So there is a water balance for the Po River shown here, which changed a lot during time. Okay, perfect. And then here you see some examples of unsustainable impacts. And keep in mind one thing, agriculture, and this is a critical issue, agriculture is responsible for the largest part of most of our water consumption. I mentioned to you 70% of the total global water consumption is for irrigation. And also agriculture is responsible for a large part of the CO2 emissions, agriculture and farming in general. And this means that this is delicate because agriculture is also an essential, it's key to human development and to a sustainable use of environmental resources. Construction of dams is another example, strong environmental impact. And then today there is several parts, several bodies and a large part of the population are not keen on building new dams. On the other hand, dams are necessary for energy production and water storage. The increased demand for energy, fossil fuels means, and then the result is that, and this is our starting point, the concentration of carbon dioxide in the atmosphere increased a lot, markedly increased during the 20th century. And here there is a big question mark, a big research question. So what is the reason for the increase of carbon dioxide? There is a large consensus. Again, consensus is a word that I don't like. We cannot measure the human emissions of CO2. We can measure the CO2 concentration in the atmosphere, but we cannot measure the human emissions. We can make an estimate. There is a large consensus that humans play a key role, so that human emissions have caused a significant part of this increase. On the other hand, it's also true that the human population is increased. It's increased in 1950, we were 2 billion, and now we are close to 8 billion. So another question is, can we reduce our emissions without reducing the human population? And then, you know, the discussion involving human population, you understand, becomes extremely sensitive because it is something that we cannot even think of controlling. I mean, or it is sensitive, more than sensitive, I would say. And in terms of CO2 concentration, maybe I already mentioned last week, when you increase the temperature, and temperature, let's suppose that the temperature increases for solar activity, so not related to humans, then an increase of temperature causes a release of CO2 from the oceans. If you warm the oceans, they release CO2. And then the CO2 concentration in the atmosphere increases. So is like a chicken and egg question. What causes the increase of temperature? It's the increase of CO2 or the other way around, the increase of temperature that causes an increase of CO2. So these are relevant questions, but on the other hand, as I said last week, for sure, limiting human emissions, now they are estimated as, I mean, this estimate is something really uncertain, but let's say that there is a prudent estimate is 25% of the global emission on the environment are likely to be caused by humans. Some of them cannot be eliminated because humans, like any living species, of course, emit CO2, and there are some parts of the emissions that cannot be eliminated. We cannot think of becoming really emission zero. Okay, and so we already defined weather and climate, so let's forget about it. What is important is to stress once again that one thing is global change and one other thing is the local change. And this gives to me, as I said, the opportunity to introduce something that is relevant to you. The increase of temperature in cities is more marked than the global increase because of the heat island effect, which you may know. It is a recent effect. The heat island effect was noticed after the expansion of cities. And the expansion of cities has been very relevant from 1960, 70. The heat island effect was first noticed, became a concern like 1990. And it is, of course, limited to cities. And the cities, in terms of extension, are a very small part of the global Earth. It can be something like 1%, maybe less, maybe less. And you can find some information on the web. I can tell you that in the province of Bologna, the urban areas are 4%, and the province of Bologna is highly urbanized. So if you think at cities with respect to the global extension of Earth, as I said, probably is 1%. But on the other hand, most of the human population lives in cities. And health problems, as a consequence, are related to living conditions in cities, much related. And therefore, the heat island effect is something that is very relevant to global health, even if it is extended over a small area. So let's go back to the previous slide. This is temperature on average over September during 10 years of these cities, and Yokohama, Tokyo, in Japan, Katsura, Maebashi, and Kumagaya. And you see that the increase is from, let's say, 21, like for instance, Tokyo, from 21.5 to 24.5, 3 degrees in September. And then if you get Maebashi, I hope I am pronouncing well, about 20.5 in 1907, 20.5, yes, and now close to 23. And if you look at the trend of Tokyo, Tokyo has increased much more. Why? Because it's a big city. The expansion has been larger. So, I mean, when we talk about 3 degrees, 4 degrees, and in some cities in the United States, they detected 5 degrees of increase, this becomes something relevant also to health, you understand? And also the reaction is air conditioning. Air conditioning is contributing to even further warming into the urban areas. So this is why now we are starting thinking of nature-based solutions, green roofs, green walls, because they give a lot of contribution, vegetation in cities to lower down the warming. This is why Milano Due is today an excellent example. And if you think that it was designed around the 70s, 50 years ago, it is indeed forward-looking, because probably they were driven by a different criteria. They thought that the global quality of life, which takes benefit from green areas, but actually it turned out to be also very important for the temperature. This is becoming something. And what is the solution here? Yes, nature-based solutions, but not everywhere you can apply them. For instance, in several cities in Italy, you can't place green roofs because of the need of preserving the cultural heritage. There are some buildings that you can't touch. You can't. And many of the buildings in cities in Italy are protected by the National Authority for Beni Culturali, for cultural heritage. And so you can't put green roofs everywhere. In Bolzano, for instance, in Bolzano, they made interesting experience with the green roofs because they could do that, because they don't have a lot of historical buildings. They have some, but for most of the buildings, they could use green roofs, and in a way they could modify the urban environment. But this is not always easy. And don't forget, we need resources. It's not easy. And in Italy, we have limited resources. So you see the debate today on the destination of resources to the public health system rather than flood prevention, rather than the fiscal, how to say, the fiscal wedge, cuneo fiscale, or it is, I mean, it is a significant debate. And so, I mean, indeed, these numbers are interesting. Now, what is the drive?
What about the surrounding areas? Like maybe you cannot put windmills in Milan, for example, because there are a lot of buildings that you cannot touch. But like if you act on the surrounding areas, or it's like the city is a microenvironment, it became a microenvironment, I don't know to say, con un piccolo ecosistema in cui...
Yeah. I don't think, I mean, the surrounding area, if you work on the surrounding areas, I think this is efficient, useful, successful to limit the expansion of the heat island. But you cannot mitigate the heat island in Milan if you work on Milan. So you can limit the expansion, but still the heat island into Milan is there. And of course, we are working, not of course, I mean, we should try to avoid that the heat island expands. And in order to do that, we are already adopting in the urban expansion plans criteria that try to promote the use of nature-based solutions. But still, the problem in the urban areas, I think it can't be solved. I believe that probably it will not increase too much the temperature. Of course, it is a big question mark, but I think that it cannot increase up to more than a certain level, but it is still it remains a problem. And what is, I think, I want to give you the order of magnitude, because then you can be able, so in some cities +5, I don't think it could be more than that. It's already the example of big cities where they didn't make really any successful mitigation action. What we can do is to limit the use of air conditioning, but on the other hand, it may be a problem. Or what we can do is to limit, for instance, the circulation of cars. And this is also useful for mitigating air pollution. Now, what is the power of the climate system, the fuel? The fuel is solar irradiance. So keep in mind that the Earth system is a closed system in terms of energy, with the only exception of the solar irradiance. Solar irradiance provides fuel to ecosystems, to life over Earth, and it's the only source of energy for moving natural processes forward. And in particular, it's the only source of energy for the water cycle. The water cycle needs a lot of energy to move. And the solar system, the climate system is fed by the solar irradiance. It can be measured. It's usually the unit is watt per square meter. It's not constant, and it's not easily predictable. We recognized some cycles, and an example is the Milankovitch cycles, which is an 11-year sunspot cycle, the Milankovitch cycle, which is related to a periodic change in the inclination of Earth. Because of course, when you, if you change the inclination of the Earth axis, you change the way Earth is exposed to the solar irradiance. And this change of inclination is one of the hypotheses that we move forward to explain the occurrence of glaciations. So this 11 cycle, cycle, the Milankovitch cycle, which I made confusion with the 11-year sunspot cycle, which is another story. The Milankovitch cycle is a cycle that we know. I don't remember the periodicity. And then there is the sunspot cycle of the sun. Yes. Please.
Sorry, I have a chat with previous slide. Are, for example, parks in urban areas that would like step back towards the urban
Yes.
islands, for example, Central Park or even
Yes, the parks in urban areas is one of the solutions, and where it is possible, indeed, we try to recover green areas inside the cities. And also, as I said, green roofs are a good solution, and they were proved to be very effective in terms of urban heat, in terms of internal heat into the building, and in terms also of storage capacity to retain water. The green roof has the problem of the infiltration of water into the building, and this is something that is a bit relevant. It's not easy. When it rains a lot, it is in other situations where you don't have much of rain, then it's fine. You have to irrigate the green roof, but in any case, you have to irrigate it. So you have to provide some water during summer. But still, the benefit in terms of water saving, has been proved to be significant. But when it rains a lot, you see that when it rains a lot, typically the roof of the houses are very steep because, keeping water out of the houses is not easy. So in general, preventing water from infiltrating somewhere, it's a big challenge. So it needs a continuous maintenance. So the green roof indeed has been proven to be a bit problematic when it rains a lot. But it is for sure a solution. And also the parks, yes. Yes, this is why in the new urbanization there are strict rules of the percentage of soil that you can urbanize. And another possible solution is the use of the parking places with the green elements, Instead of paved with asphalt, now you increasingly see permeable pavement because the grass that grows up in this permeable pavement is very useful. You had a question?
No, I was saying that I remember I've heard about Bosco Verticale.
Yes, yes.
And the fact that after maybe 2 years that there was an invasion of bugs or something like that. And maybe this is also something that could happen with green roofs.
Yeah, of course, you have to. There are some implications in terms not only of the filtration of water, but also in terms of, as you said, of bugs. And this is something that may be relevant in certain environments. In our cities, I didn't get any information of negative implications in that respect. But of course, it depends on the location, because it could be also vectors for vector-borne diseases, like mosquitoes, for instance. It's a bit of yeah, what is your question?
I wanted to say something about Bosco Verticale and maybe ask some information about it. A good friend of mine lives in Bosco Verticale, and unfortunately, they've been complaining of having to do massive work.
Sorry, massive?
Massive work, construction work, even though the building they bought in 2014, so they're really like 10 years old, so relatively new. And the problem is they've been complaining of structural problems because when the water goes into all those massive gardens, obviously there is a very, you're the engineer, so I don't want to say imprecise things, but there is a really strong change in obviously the weight. And so he's been telling me that they have to do some sort of work to make sure that it gets more resistance. Otherwise,
okay, yeah. Bosco Verticale, you mean green walls, correct? In the buildings. Okay, perfect. Okay, and then okay. Via Garibaldi in Milan. Okay, no, I'm not aware of that. But usually I use the term parete verde, green wall, and in English is green wall. But yes,
building of
I'm sure you've seen it. The Via de Castilla. No. Of course. Yeah. One of the most beautiful skyscraper in 2015. That's
E attorno c'è anche un parco, quindi l'aria verde
avrà sicuramente. E proprio si lamentava lui che è una di queste unità, diciamo, su famiglie, ecco, che comunque c'erano dei grossi problemi strutturali, dovuti alla grande quantità di acqua che entra e esce con tutte queste piogge.
You know, these are relatively new experiments. And because, as you said, 10 years old, and of course, in engineering, we have the means for designing structures that can sustain any load. The problem is load estimation and design variables and load estimation. So, you know, maybe that I'm not an expert in these solutions. I am sure that they are still collecting data on the benefits in terms of retained water. They are still getting data on that. So I'm not surprised that they probably are still getting data also on the loads. So in this case, maybe that they had to reinforce the building because the loads were underestimated. The loads means the weight of the water that is retained. So if they don't have any idea of the water volume that can be retained, and also, you know, also any idea on the development of the ecosystem, this means that they have not a clear idea also of the loads.
Couldn't it also be a problem of the green roofs?
I would say that with green roofs, in my opinion, it is easier because it's horizontal. So it is water stored. And during a vertical wall, I'm just reasoning with my intuition. As I said, I'm not an expert, but with the vertical wall, I think that the weight of the wall, the quantity of water stored into the wall, may be more uncertain, you know. And water has a big problem that is very heavy. We don't realize it, but it's very heavy. And it is the load of water against a wall can be really very heavy, more than the self-weight of the wall itself, because the wall is like 30 centimeters, 50 centimeters. But the water, it's the specific weight is a bit lower than the concrete. But the amount of water that can be stored by vegetation and by a green wall, it's really a significant amount. So it is, I'm not surprised that probably the experience is still developing. And, but they are, I mean, they are interesting, and also the durability. We know that the durability of the structure is compromised. I mean, in older times, people always recommended don't allow vegetation to climb over a wall because the durability of the wall is compromised. It is damaging. So, I mean, these are all solutions that need to be carefully planned and studied, based also on the experimental results.
So I've been told that you're trying to add it from the news, but actually many of the residents have been having to avoid depreciation of the unit. Been trying to idle, but many of the residents are having problems with
Yeah. I'm not surprised. As I said, I had some experiences with green roofs. And indeed, it is a bit of a problem. And also, it is a bit of a problem in certain climates where you have a huge difference of temperature between summer and winter. Then the problems with green roofs and green walls are more relevant because also the structures of the buildings with the thermal expansion, you know, they are subjected to a significant additional thermal load, let's say, of sollecitazione termica, I mean thermal load, and I don't know how to call it in English, but okay, you understood, you got the translation. And therefore, I think that also in terms of the water weight and in terms of the dynamics of the ecosystem, I mean, the most favorable situation for a building is when the situation is stable. For a building material, when you have a stable condition is the most favorable. For instance, we always tell our students, if you use wood, wood is very durable if it is always wet or always dry. But wet and dry, durability of the wood is going away. Yeah. Did I answer your question? Yeah, or yeah, okay. Okay, so solar irradiance. And second, I mean, you have measures of the solar irradiance from the Global Solar Atlas by the World Bank. Solar irradiance may also be useful, a useful information for the health problems. And these links are working. Let me see if it's still, yes, I think so. It's still valid. Yeah, still valid, okay. Okay, then another important driver, the greenhouse gases, who are responsible for the greenhouse effect. So greenhouse effect, let's open this link. I'm not sure if it is, here it is. So what is the greenhouse effect? Okay, we get the solar irradiance, some sunlight that hits the Earth is reflected back into space, while the rest becomes heat. And the greenhouse gases absorb heat and redirect it towards Earth. It's like a greenhouse. And there are several greenhouse gases. CO2 is often mentioned, but also water vapor is a greenhouse gas. Methane is very important. And others. Water vapor is a very relevant greenhouse gas. It has the advantage that its residence time in the atmosphere is much lower than the residence time of CO2. And therefore, why CO2 is and methane are our main concern, because with the long residence time, you understand that if you emit more CO2 and CO2 remains in the atmosphere for a long time, there is a continuous accumulation. So it may happen that in some seasons, in some very limited periods, the water vapor has an effect on the greenhouse effect that is more relevant than CO2. But then water vapor decays rapidly. CO2 remains there. There are a lot of information over the web to give more details. I think that what is important to know from your side is that the CO2 concentration is increasing continuously. And this is the reason why, for sure, the greenhouse effect is relevant. And this is maybe also the reason why in the cities this is amplified, because probably without the greenhouse effect, we wouldn't have this amplification in cities. So whatever is the reason, so let's suppose that the reason for the increase of temperature is sunspot activity, because as I said, we still know we still know very little of the sun activity, and we cannot predict it. So we cannot exclude that the global warming is due to an increase, to a cycle, an increase of the sun activity. We cannot exclude it. But still, I mean, if take this hypothesis, the increase of concentration of CO2, however caused, gives, as a result, the greenhouse effect. And the greenhouse effect is a positive feedback, is a reinforcing feedback, okay? Okay, let's go back here. So you didn't see the picture of, no, okay. Sorry, I thought that you saw on the screen a picture that I'm showing it to you. 1 second, I think I need to, and then I make the break. Just 1 second. Okay, this was, I'm not sure, let me see. No, still not working. What is that? Ah, because it's a PowerPoint. Okay, I see. Just 1 second. Good. Okay, this was the figure I wanted to show you. And this is available on the web. If you look at the Wikipedia page, greenhouse effect, there is a description which gives you more information, and there is this figure here. And if we go to the Wikipedia page, by the way, just 1 second, it's here. I think there are other figures. This is too much for you, even for me, but I was looking for figures. Anyway, it's, let me see, greenhouse theory. Greenhouse effect, let's see. Okay, I wanted to, I get another figure to you, just 1 second. Here I have a lecture on climate change and water cycle that if you want to see, to get some very easy information, and there are a lot of figures and information numbers. So you see that solar radiation, and this is an estimate of the total of an average value of solar radiation, 235 watt per square meter. And here you have an estimate of the average temperature of Earth, which is 14 degrees. I'm not sure if I gave to you this number earlier, but keep it in mind. And then here there is an estimate of greenhouse gas absorption. And this is a balance, basically. And these numbers are estimates. And in order to understand these numbers, you have to look at the whole cycle. And the whole balance is breaks even. But I don't think we need to go into the details. And I think, yeah, this is the figure that I wanted to show you. Okay, now let me go again here. Perfect, and let me share the screen. So basically, when I am in PowerPoint presentation, okay, the screen only sees, let me see what is shared. Let me see. Okay, that's fine. Perfect. So in terms of emissions, then, you understand that if the greenhouse gas is a relevant driver of climate, and of course we assume it is, because this is the explanation that climate models give for global warming, then it is important to make an estimate for the future. If we want to make a predictions, it's important and necessary to make an estimate of the future emissions. And the IPCC worked a lot on that. And here you can see a graph which shows to you, and this graph, let me see if it is okay. You can see the numbers of the dates. Basically, today is where the several cards depart, and they depart in 2015, because actually these were predictions issued in 2015. So you can see that you see that there is a unique curve, black curve up to 2015, and then from 2015 you see different predictions. And these are greenhouse gas emissions expressed in gigatons. The vertical axis is global, and in gigatons, and these are the estimated human emissions. Now, you may see a kind of inconsistency, because I told you earlier that we cannot measure human emissions, and I confirm this. It is not measured. But in this case, what we have done is to make a prediction through socioeconomic scenarios. And of course, we assume that to a corresponding socioeconomic scenario corresponds a given amount of CO2 emissions. And so it is an estimate. We cannot measure, but we can estimate, okay? And in the same way, when I said human emissions are estimated to be 25% of the total, it is an estimate. Human emissions cannot be measured at the global level, but still we can set up models and estimate them. It's like future temperature. We cannot measure it, but we can set up a model and make a prediction. And so here you see that there is a pessimistic prediction with no climate policies, and it is assumed to correspond to an increase of temperature, global temperature, up to 2100 of about 4.1, 4.8 degrees. And then there are the predictions of which correspond to several mitigation policies. If you see at the current policies, then you get to the orange band, which predicts an increase of emissions up to the cap, and up to a cap, and up to a top, and it is estimated that this top is reached with the current policies around 2040, 2050. And then there are other estimates, and there is the Paris Agreement target, which is the dark blue one, or sorry, it's the pledges and targets, it's emissions, it's an intermediate prediction between the current policies and the Paris Agreement target. The Paris Agreement was reached during the Paris conference, COP, I don't remember the number, where states agreed on setting a target of max 1.5 temperature increase. We are very close, actually, we are already 1.3. And then as a backup target, they also agreed that 2 degrees is the max, absolute max that we shouldn't exceed. And these are the 2 emissions targets corresponding to the Paris Agreement, the green one and the dark blue one. So these emission scenarios are used as an input to climate models. Would you prefer to make a break now and then we move forward? Okay, then I stop to 6:15. Okay. Okay, good. Okay, and here also you see other reasons of other forcing and feedbacks. Aerosols, we mentioned them last week. Actually, aerosols has a cooling effect, and here there is the definition of feedback. So a feedback that increases an initial warming is called a positive feedback, a reinforcing feedback. and a feedback that reduces initial warming is a negative feedback. Let me give you an example of negative feedback, which we thought that would be able to compensate the global warming. An excellent example is clouds. With global warming, we supposed that we should observe an increased evaporation, so an increase of cloudiness, and cloudiness reduces, of course, the solar radiation, and therefore may compensate global warming. Actually, what we observed is that after global warming, evaporation did not increase. And this is something that we are still learning, but there are increasing studies demonstrating that evaporation at the global level through measurements, it's not increased. And this originated the so-called evaporation paradox, because at the beginning we didn't have, still today, we don't have a satisfactory explanation. Probably the reason is that there has been a slowing down of the average wind velocity. Evaporation is favored by wind. So when you have a lot of wind, you have more evaporation. So probably there has been a slowing down of the wind velocity, which has in a way compensated the evaporation, which is not increased. And therefore this possible negative feedback contrasting global warming, actually we are not sure that indeed took place. But let me tell something more about feedbacks. So here is, here there are some examples of feedbacks. So, for instance, in terms of precipitation, global models show that precipitation will generally increase due to the increased amount of water that is held in a warmer atmosphere. But actually, with the awareness that evaporation didn't increase, then we are not really sure whether we may expect more precipitation and in response to global warming. In fact, if we look at the average precipitation, we generally see that there is no change. But it looks like maybe that precipitation is more concentrated in few events that become more extreme. So maybe that the total is not changed, but on the other hand, it looks like short-term precipitation is increased. Now, what is the effect of forest greening and browning? So natural processes, such as the growth of forests, remove about half of human carbon dioxide emission, these are estimates, from the atmosphere every year. And there are a lot of studies now trying to better quantify this effect, because there is the feeling that with more CO2 in the atmosphere, there is more activity of vegetation, because CO2 is a fertilizer. And therefore, it is supposed that this increased acceleration of the life cycle of vegetation may contribute as a negative feedback to absorb CO2 from the atmosphere. So the idea, the hypothesis is, the research question is vegetation compensating, is vegetation acting as a stabilizer with respect to the increased CO2 emissions by humans? Of course, one may expect that vegetation has been reduced by human activity, but actually, if you look at the global coverage of the world, there are still the major part of the Earth is still covered by vegetation, which may have accelerated, indeed, may have increased the total mass of vegetation and therefore the absorption of CO2. Ice albedo. Ice is white and very reflective, in contrast to the ocean, which is dark and absorbs heat. So as the atmosphere warms and the sea ice melts, the darker ocean absorbs more heat, causes more ice to melt, and makes Earth warmer overall. So this may be a positive feedback, but still our understanding is limited. Water vapor, the most abundant greenhouse gas, it's a feedback to amplify climate warming forcings if the evaporation increases. And here you have an example in this figure. So positive feedback, snow cover loss, water vapor increased if evaporation increases, which is now seems that didn't increase. Melting permafrost, which releases methane into air. This is another feedback that is significant. It's believed to be significant. And then negative feedbacks. Warmed Earth radiates more infrared into space. And plants remove carbon dioxide from the air, I just mentioned. Oceans remove carbon dioxide from the air. This causes ocean acidification. But of course, ocean may remove. I'm not saying that they remove, because after warming. Your question?
About the negative feedback on plants. I heard about the fact that plants during lifetime absorb CO2, but during nighttime, so without light, they release
Yes.
CO2. So is this feedback more prone toward the absorbing of the CO2?
Yes, the presence of plants overall is they absorb CO2 overall. And there are a lot of researches, as I mentioned earlier today, on quantifying this effect. But it is overall, the balance is positive. So they absorb more than they release. And we have to be careful about the CO2 emissions of trees during night in closed environments. So this is why we are told that don't put plants in your sleeping room, because indeed during night they release CO2. But overall, the balance is positive, and this is why also greening is important. There are really a lot of researches. It is a very hot topic. A lot of research in trying to better define the carbon cycle. The carbon cycle is one of the key players in the Earth system, in the climate systems, and it is still not well defined, like the water cycle. But the carbon cycle, indeed, it is probably even more complicated. And there are a lot of researches that they are making through experiments in the forests, but a lot of research projects. This is really a very hot topic, because it is aimed to improve the representation of climate models, because climate models, they need this information, of course, and they need this information in a spatially distributed way. Okay. Climate change attribution, there are also a lot of studies, and I think here there are two nice videos linked, and very easy. And they are like dissemination videos, and they are interesting because they give an overview of climate change evidence. I'm not playing them now because they are short, like 5 minutes, but I think these are more for your personal, personal study if you want to expand your knowledge. And one is providing evidence for climate change. The other one is talking, it's very interesting because it's talking about ice ages and climate cycles. And so basically they give you an overview of variability and change, which is from the same producer, and I think they are interesting. Okay, and so let's now get into the discussion of how climate is modeled. And let's start from a very brief history of climate science. So when started the humans to be concerned about climate change? Earlier than you may expect, already in the 19th century. And why? Because first of all, they discovered at that time ice ages. They started studying the ice ages, and therefore, of course, people got concerned, because when they realized these huge changes in climate, people got concerned for their personal safety. And also there is one thing to say, that in the 19th century, people realized that climate was changing because we had in the a little bit earlier, around around 1750, the Little Ice Age ended. The Little Ice Age was a cool period that lasted from 1400 to 1800, and a little bit earlier than 1800. During that period, there was an expansion of the glaciers in the Alps. There were several floods, and I mean, people got really used to, people were not skating but they were walking on the Venice Lagoon over the ice, not skating, but they were playing there over the ice in the Venice Lagoon. And there is a famous picture in 1650, I think, of the Venice Lagoon that was iced. They were used really to hard conditions, and they realized around 1750 and from 1750 to 19th century, so that in these 100 years, climate was changing, was warming up. Indeed, the warming started with the closure, with the end of the Little Ice Age. If you are interested, you can look on Wikipedia, in Italian and in English, Little Ice Age or Medieval Warm Period. These are two known temperature oscillations that occurred in the past 1,000 years. And then in the 19th century, the Industrial Revolution came, and people got much concerned by the quality of air pollution, and they got the first health problems due to air pollution. And therefore, they realized the climate was changing, the socioeconomic setting was changing. So the scientific community became concerned about climate change. And in 1960, after the economic boom, evidence for the warming effect of carbon dioxide became increasingly convincing. And the greenhouse gas theory was launched, if I'm not wrong, around the end of the 19th century. So, I mean, the concern about the human influence on climate, in general on the environment, started after the Industrial Revolution, started in the 19th century, and then developed, grew up. And up to today, when we realize that air pollution, indeed, we are taking mitigation actions of this risk. We realize that global warming is causing what we are discussing, etc. And people today are getting more and more aware that natural variability of climate is, on the other hand, still poorly understood. So on the one hand, there is an increasing belief that humans are modifying climate. On the other hand, there is also an increasing awareness that we still don't understand this natural variability. And this is why people are dedicating, the human species dedicating a lot of research efforts to understand past climate. Paleoclimate studies by the use of proxy data like ice cores or tree rings. We will talk about these. So exploring, getting climate data is becoming a very relevant, interesting research question. Just because we want to understand what is the role of climatic variability.
Do you see patterns as a history of climate changes, or you think it's around?
What do you mean? You mean climate change, past climate change?
Yeah, exactly.
Okay.
Like
Okay.
thinking about I mean, when I think about studying history, is to learn, like the pattern, like learn something.
Yeah, indeed. No, this is precisely what we are exploring now. So the reason why we are getting entertained by these climate paleoclimate studies is that we try to understand what was the reason of ice ages, etc. And indeed, what we have observed so far is that there are patterns. There are patterns like droughts that lasted 1 century, and there are also connections between the number of floods, for instance, flood frequency and temperature. We are understanding more and more the patterns and the connections. About the drivers, there are still several hypotheses that are being explored, because the drivers may be impossible to measure. So one possibility, for instance, is that these climate changes were only local and not global. And like the medieval world period or the Little Ice Age, people say it's probably a European case, not a global case. And on the other hand, I mean, of course, it is difficult to verify because the data are only located in certain locations. But on the other hand, even if it was a local case, it would be, for this reason, not significant. And another possibility is that there were changes in the inclination of the Earth's axis. You know, it is possible that for the impact of meteorites or for other reasons, the Earth's axis has changed a little bit its inclination, and this is the cause of a 100-year drought, or which is local, and this is fine, and may be caused by this, or orbital changes in general. Like, because, you know, the orbit of the Earth around the Sun may be subjected to disturbances, changes. Another possibility is the volcanic eruptions. And the volcanic eruptions, even in this case, it is, you may know that it is one of the possible causes of the extinction of the dinosaurs, because, but we cannot really reconstruct these events that occurred in the past. And to give you another example, if you look at the surface of Mars, which we know very well now, I studied it, I tell you why, because by studying the shape of Mars, we could quantify that there was a lot of water, because it's clear. There are valleys, there are forms that were created by water, and a lot of it. On the other hand, what you see now, it's difficult to interpret because there are a lot of craters originated by the impact of huge meteorites. And this is impressive because why on the Earth you don't see these signs? Because there is atmosphere. So the Earth probably has had the same impacts in the past, but the erosive action of the atmosphere has cancelled them. And for the Earth, the history of the Earth, we know something for the past 3,000 years and not for the whole Earth. So it is really, we know nothing. Mars has been without atmosphere for billions of years. So this is why we see the impact of meteorites. And they are so frequent. And this is a bit amazing because it means that sooner or later we will get it. And probably with our capability to observe it, we will know like 10 years in advance. And what you can do with the huge one, it's amazing. And so this is the one possibility, an impact of a meteorite that caused a perturbation that maybe was compensated 100 years later, and maybe the impact occurred, I don't know, in the poles, and people didn't know 1,000 years ago. They didn't know of the American continent. So if there was an impact there in the Americas, like in 1100, that caused like a movement of the Earth's orbit, a perturbation. And then in the long term, the perturbation is compensated because, you know, the orbit is governed by the mass of Earth, the mass of Sun, the mass of the planet. If you get a perturbation, then after maybe, I don't know, 10 years, 100 years, it's compensated. But we cannot say that. So it is indeed something that we can see. And I will tell you about something about the paleoclimate data. It's very interesting, but on the other hand, to find the motivation, but still to know that there were these cycles is extremely important. Okay, let me see. Let me just make. Well, I think this one, it's already okay. I mean, it's talking about the science of climate change, and we already introduced it. Let me just look at the next one. Okay, this is something that we have to discuss next week. And not next week, actually. We have a break now. Let me just see what is... Okay. So in next lecture, we will start from tipping points. And I say this in the video because in this way I remember, because otherwise in a month. And then I will give you the next lecture some information related to climate models, and then we will get into the discussion of climate-induced diseases. Any question? Any more question? You are very interactive. Thank you. This is really stimulating and also helps me to get more entertained into the lecture. Ok, perfect. Grazie. No, avete un'interattività alta.